Hi, my name is Dan Davies from the Hirose Laboratory. I'll be presenting my research on the development of an 8-legged autonomous vehicle for loaded stair navigation. This will be the outline of my presentation today. I'm going to start with the motivation behind the research. As many of you know, Japan is a hyper-aging country. It's got a rapidly aging population, and this is going to correspond to an increasing number of wheelchair users in the near future. This has spawned a lot of research into, these are some of the government-passed regulations that are meant to improve the accessibility of public areas. Mainly stair rails like this and elevators are being installed into large department stores and train stations. However, not all buildings are able to accommodate large lifting equipment, such as this station in Tokyo. So this has spawned a lot of research into some mobile stair-climbing vehicles which are able to carry a wheelchair and a passenger upstairs. I have a couple of videos here I'd like to show you of commercially available vehicles which are designed to carry wheelchairs upstairs. There are basically three different kinds of research in this field: wheeled, crawler, and legged. Basically, the wheeled and crawler vehicles tend to load the passenger in a rear-facing direction. So the passenger can't see where he's going. This is kind of a problem with these. Also, there are legged vehicles such as these. However, they tend to have an oscillatory motion, not a smooth climbing motion up the stairs. This can also lead to a little bit of uncomfortability for the user. There's also some research that's being done in our own lab. This is a vehicle called Zero Carrier. It was built about 3 years ago. It has four drive wheels on the bottom and 4 passive wheels, and it climbs up the stairs in this alternating zigzag pattern. It's also not a smooth ride. So this leads to my own research. This is our proposal. It's the same mechanical design, except it can accommodate the wheelchair in the forward-facing direction. The aim is to climb the stairs quickly and continuously with a smooth, continuous stair climbing motion, and also accommodate a wheelchair. This is the mechanical design of the vehicle. I'll just go right into explaining it. This is the leg drive mechanism. There are 8 of these to drive the 8 legs that are attached to the vehicle. And it uses a timing belt drive mechanism. The advantage of this is that you can have a small, compact drive mechanism that can drive a leg of any length. This is a picture of the old mechanism that we used by the first vehicle. It's a change of a mechanism. And the disadvantage of this is that the drive mechanism has to be as long as the leg, since this attachment point has to move up and down the leg. This design stands stationary as the leg moves up and down, so it can be a lot smaller. And then this up here is a timing belt tightening mechanism, which is used to keep the belt taut over the length of the leg. I'll talk a little bit about the wheel layout considerations. As I mentioned, there are 4 drive wheels and 4 passive wheels, and there was a lot of consideration given to the relative positions of these wheels. With the first vehicle, there was an alternating pattern of passive drive. With this configuration, there can arise a situation shown here and here where both the drive wheels have to lift up to meet the next stair. When this happens, none of the drive wheels are in contact with the stair surfaces, and no forward propulsion can be produced. So, where should the drive wheels be? This is the center of rotation of a wheelchair. And as you can see, it's right in between the 2 drive wheels of the wheelchair. And this is a top view of the vehicle when the wheelchair is on it. In order to have the same center of rotation as the wheelchair, the drive wheels should be here and here. This is the front of the vehicle, this is the rear. We need drive wheels in the 3rd pair of wheels in order to have the same center of rotation as a wheelchair. This can provide a more intuitive control for the passenger. So, the drive wheels are located here in the very rear of the vehicle. This allows all of the drive wheels being in the rear lets us ensure that at least one pair of drive wheels is always in contact with the stair surfaces, even as it climbs up the stairs. A situation where all drive wheels have to be raised to climb the stairs doesn't occur with this layout. Also, we have a center of rotation here in the rear of the vehicle. Also, I forgot to mention that normally you want to have drive wheels at all four corners in order to support the weight of the wheelchair and ensure that you have sufficient traction for all the wheels. However, the center of gravity of the vehicle with the wheelchair is slightly towards the rear. So there is sufficient normal force on the rear side of the vehicle to provide forward locomotion. Next, I'll talk a little bit about the passive wheel. I mentioned there are 4 passive wheels on the vehicle. Normally, just a regular passive wheel that can rotate 360 degrees would be sufficient, like on a wheelchair. However, in this case, we have to raise the wheels as we climb up the stairs. What happens when we do this is that this passive wheel is allowed to rotate while the leg is raising. We don't know how far away the wheel is from the next step. So this presents some control problems. So what we want to do is control this wheel in a fixed orientation as it's raising, while still allowing the free rotation when it's on the ground to allow zero radius turning. So this is the proposed mechanism. It consists of 2 basic parts, a circular cam, which is free to rotate around, and a cam follower. These are 2 situations that the mechanism can be in. First, this is the free rotation state, where this cam follower, which is fixed to the leg, is off of the circular cam. The weight of the vehicle is pushing the entire leg down and making the cam follower come off of the circular cam. The other state is when the leg is lifted, as in here, as shown here, and there's a spring at the top of the mechanism, which pushes the circular cam down onto the cam follower, forcing it into a fixed orientation. I'll show some results that were taken from an experiment with this mechanism. This is the mechanism attached to the leg. As you can see, when it's on the ground, it's free to rotate 360 degrees. And as it's lifted, it's locked into the fixed orientation. Originally, we had the idea of attaching a spring between the wheel and the leg. However, this would not allow the wheel to it wouldn't allow infinite rotation around the leg. You would only be able to turn to 180 degrees before the spring would get caught on the axis of the leg. That's the reason why we came up with this mechanism here. I'll move on to the sensor. The old zero carrier used distance sensors to measure the positions of the stairs. However, this forces the vehicle to approach the stairs before measuring the dimensions of the stairs. What we want to do to implement this smooth control is to know the dimensions and locations of the stair sets beforehand. So what we did was use a laser rangefinder to view the stairs from a distance and then calculate the locations of the stairs. The way this is done is, well, this is a view of some actual data points taken from a set of stairs. All the data points are